Yeah, so today I want to talk about a package that I've been working on for a couple of years called IQMon. And so I wanted to motivate this a little bit. Prior to my work at Subaru, I worked in small automated telescopes. And this is a fantastic tool that's still relatively new to astronomy, and it really enables sort of small projects, with just a handful of people and relatively sparse funding, to do time domain science. And the problem that at least one or two projects I've been involved with has encountered is that it's relatively easy nowadays to build a system that will operate every night and generate a whole bunch of CCD images. And the trouble that we ran into is that we didn't really have any way to monitor how well the telescope was actually performing. And so I talk about here that we generate large amounts of data. So we've heard a lot about big data at this conference, and that is definitely not what I mean. In this case, large is basically generating data at a rate that it's impractical for a human being to check it as it comes in. So as I mentioned, I worked on one of these projects as a postdoc, and I basically built the hardware and installed the control system. And so this thing was up, it was running, we actually had 2 telescopes, and that was it. I didn't know, how well the system I had put together was performing. I needed to know if I needed to tune certain parameters, if there was tweaking that needed to be done to some of the control system. So I wanted some way to monitor the image quality coming out of the telescopes, and this was also the project that I used as an excuse to teach myself Python. Like a lot of scientists and especially astronomers, I had done some IDL and IRAF and things like that and wanted to get out of that sort of environment into something that was freely available and very general. And so this was how I did it, was basically force myself to use Python for this project. So what I'm really trying to do with this is I'm not trying to do a full data pipeline. We've heard a little bit about data pipelining here. What I want to do is do just enough data analysis to answer some basic questions and no more, strip everything out that I possibly can. So really the things I want to know is, when did the telescope observe? Which, okay, I can sort of find that out from the logs and just looking at file system, looking at the timestamps on the data. But I want to know, was the telescope in focus? Was it pointed correctly? Was it tracking correctly? And was the aperture obscured in any way by clouds or by a mispointed dome, for example? So I need to do actual image analysis to answer these questions. So I came up with this IQMon package, and so the goals that I'm trying to meet here is it should be really simple, again, because I was learning programming, basically. And it should be at least somewhat informative. I want to be able to differentiate between different problems so that I can look at the results and know, okay, it's probably this went wrong. And I want it to be automatic, so I don't want to manually spot check the data, which we had done briefly for a little while once we got started. And it should be essentially what I'm calling near real time, which is basically that it should roughly keep up with the data flow, and I want it to be available when I wake up in the morning so that I can pull up, say, a web page on my phone even and find out if I've got troubleshooting work that day. So the other goal here is that I don't want to reinvent the wheel. I want to make use of existing tools. So as you might imagine, in Python I use a lot of AstroPy, PyFM, I use AstroQuery, several other packages. But I also use several other non-Python programs, and we'll talk about them a little bit as I go through a quick example, but astrometry.net, Source Extractor, SCAMP, and SWARP are the big ones there. So how is the package structured? Really, it's got 2 key classes that are defined. So there's a telescope class, which just contains, it's very simple, just basic information about the telescope that was used to acquire the data. And then there's an image class, and that represents a single astronomical image. And so all of the analysis that this does are basically just method calls on that image object. And so conceptually, IQMon works only on single images. So there's no concept of image sets or visits or anything like that. So we're not combining data to find out what the sensitivity is over a range of, a stack of 3 images or 5 images. So it's single images only, and that was one of the simplifying assumptions. So IQMon is basically this package, and if you want to analyze an image, you just run a series of these methods. And so I'm going to step you through a very simple example. And the way it's sort of envisioned that you'll use this is that you write a very simple script, which I've called, in my case, measureImage.py, and that will just define everything and make these calls. So first thing is we want to import IQMon, and then we instantiate our telescope with a configuration file. So this is just a YAML formatted file that contains the basic parameters of the telescope, and then there's a bunch of sort of configuration parameters for the operation of the program. So I don't want to go into the details here, but this is what it looks like. It's YAML, which I like because you could put in comments. It's got some path information, basic information on the telescope, focal length, that kind of thing. And then if you want to dive a little bit deeper, you can set a whole bunch of configuration options that get passed down into these third-party programs that get called. So you can set up Source Extractor and some of those programs here. So once we have a telescope object, we instantiate an image object by just pointing it at a file. And then we also pass in the telescope used to take that data. So the other thing that I tried to do here is I used the logger as sort of the main way to show the user what was happening. So I've tried to make all of the logging in here very human readable, and so very clearly states, I'm now doing this step is done, here's the results. So as you're doing this interactively, which you can do, then it tells you exactly what's going on. So you make a logger with a simple call to the image. And then first step is to read in the image. So this actually looks at the image on disk. And one of the other principles was that I didn't want to operate on raw data. So it just reads the image, and then it does all its work on a copy of that image in some sort of temporary working directory. And the other thing I'll mention is that, of course, it works on FITS files, which are the common standard for astronomy. But I'm also working on a project where we're using digital SLR cameras to do wide field photometry. And so the IQMon works with DSLR raw files. So you can bring in a CRW or DNG file, and it uses a piece of third-party software called DC Raw, which some of you may have encountered, which is neat because you can actually get linear data out of it, so you can do actual photometry. So we read in the image, it makes that copy. In the example I'm showing here, it's from a telescope that has a single mounted filter. There's no filter. We also add the filter information to the header because we're going to need that when we do photometry. And then I read the FITS header in so that it, again, just has some basic image properties. There's a couple of options. So for example, in the top here, I've got a crop method. So you can crop down the image to work just on, say, the inner few megapixels. And I can just do that based on whether or not a region of interest is set in the configuration. And then now we're ready to go in and do actual image analysis. I use the Source Extractor program, and what it does, it looks at the whole image and basically marks as sources or stars groups of pixels which are connected together, which are all above a certain signal-to-noise threshold, and then it gives you back a catalog of information about those. So I just directly call Source Extractor and read in the catalog data with, in this case, roughly 2,500 stars in it, and then run a determine full width half max, which just goes through that and spits back out at me the typical full width half max and ellipticity of stars. So we can go beyond that, and if you want to do astrometry, there's a method for calling the astrometry.net solver. So astrometry.net is a blind astrometric solver. It'll look at the stars in the image and with no other information figure out where you're pointed in the sky. And then you can just do a simple comparison between the RA and DEC that are in your header and the RA and DEC you calculate from the world coordinate system for the center pixel of the image, and that's your pointing error. So the next thing I want to do is actually photometry. So I want to get the measured brightness of the stars and match them up to the catalog brightness of stars. So in order to do that, I need to do in most cases, a more sophisticated astrometric solution where we fit the optical distortion in the image. And so there's a bunch of different ways to do this, and I picked one particular set of tools here, and I know there are some other ways to do it. So eventually I'd like to add those back in here, but right now this is sort of the only way that IQMon does this sort of fitting of the distortions, and that's using a tool called SCAMP. So again, what SCAMP does is it takes a source extractor catalog of the stars and matches them up to a downloaded catalog from, I think you can select one of many. So the next problem you run into is that there are several different ways of encoding distortions in FITS headers. So to get around that, what I've done is I call another program called SWARP, which simply remaps the image pixels based upon the distortion solution calculated by SCAMP. So once this is done, I've got an image that's been remapped such that I can ignore distortions from then on, and then I know that any program that I want to use to examine this image will not have to deal with which distortion encoding system it knows or doesn't know. So once you've done SCAMP and SWARP, you can do photometry. So we can call get catalog, which just uses the Astro Query tool, which some of you may be familiar with. And we can look at the catalog data. It just comes out as an AstroPy table. So we've got position, ID, brightnesses, and various filters. And then I'm basically just going to rerun the photometry, and I'm going to ask Source Extractor to associate the stars in the image with the stars in the catalog. And then we can redetermine the full width half max if we want, and then measure the 0 point, which is just that offset between the measured and catalog values. And we can get all of those. So at the end of this, you've got the results on an image. And all of these are stored as properties of the image object. They're AstroPy quantities, so you can manipulate them with units. You can convert between pixels and arc seconds if you want to report your full width half max. And one thing I'll mention real quick is that, first of all, it also sets up the set of flags. So in your configuration, you can set thresholds for a bunch of these values. So if your full width half max is above a certain threshold, that image will be flagged. If the 0 point is above or below a particular threshold, you can flag it for that. And then all of these results, you can store them in a few different ways, but the preferred way is to use a Mongo database. So there's a method to just put this all into a Mongo document. So now what I want to do is get all of this information that hopefully has been collected automatically all night onto some nice web interface so I can do my lazy thing of waking up in the morning and know whether I've got work to do. So I've included in IQMon a simple Tornado web app. It's got two handlers. One gives you a list of UT dates or target names. It actually works both ways. And that gives you a link for each date of a list of images of that date. And then, of course, the other is the list of images, which shows you the image results. So it's just a big table of results. So here's what that looks like. Here's a list of UT dates, so you can go ahead and click on them and look at the image results from each date. It's also, I've got shown here that there's a PNG file you can link to. Once you have everything in Mongo, it's very easy to make plots like this. So this is from one of our telescopes. This is basically a report on one particular night. So the left column is basically weather information, temperature, humidity, cloud cover, wind, that kind of thing. And then on the right, you've got image quality as a function of time over the night. So I've got full width half max as a function of time plotted, 0 point, ellipticity, and pointing error. And you can get into a lot of interesting analyses. I don't have a pointer, but in the lower right-hand plot, you can see that some of the images, or some of the sequences are sort of diagonal to the upper right. That's my pointing error. So as I dwell on a particular target with this telescope, my pointing error slowly increases. I've got a slight tracking error, so I know right away that I should look at what my tracking model is. Here is the list of images that you can look at. And so you've got the images listed, ordered by time. You can link to JPEGs of each image, which you can create. There's a method for creating JPEGs. And you can also link to a couple of analysis plots, which I'll show you in just a minute. But then the key is those 4 green columns are the full width half max, ellipticity, pointing error, and 0 point, respectively. And they're color-coded based upon those flags that I mentioned. So this is an example of a night where things operated well. This is another night where there was a problem at the beginning of the night. And I can tell at a glance that the problem resolved itself after about, 4 or 5 images. And it turns out in this particular case, I can click on those image links, and I see that what happened almost certainly was that the dome was partially obscuring the telescope aperture at the beginning of the night, but then it must have crossed a home switch and then synced itself up again because the rest of them were clear. And you can see it again, especially in the 0 point. There was definitely obscuration, but there were glints off the edge of the dome, so it affected both the full width half max and ellipticity as well. So here's just an example. You can create JPEGs like I mentioned. You can annotate them in various ways. That shows the pointing error difference between the yellow crosshair and the blue. You can look at, this is an analysis for a single image of all of the image quality values. So you can look at the histograms, you can look at the spatial distribution of your PSF over the image, and then in the lower right, you can actually look at the correlation between, say, the angle of the PSF in the image and its position within the image, which allows you to differentiate between something like tracking error and optical aberrations. So you can actually, without diving into the image, just looking at this report, tell that we had just a little bit of tracking error on this night because there's a vertical component in this. So in conclusion, I'm hoping, kind of like the talk just before the break, to recruit users for this. I'd like to see it, see how other people use it. It's been used on 3 different telescopes so far, and in each case it's always provided useful diagnostics about the operation. So there's a paper in the proceedings, source code is on GitHub, and then you can see an example of how it's used with all the sort of customized stuff for the Visos project, which is that other link. Thanks. So the question is about setting the parameters for something like source extractor, or whether it has to be customized. It depends a little bit on your goals. I found that even on some pretty disparate telescopes, I could just use the same settings. But again, because I'm not trying to get scientific results out of this, I just need to grab enough stars that I can make a measurement. So I don't care if I get all the stars. So I can be very conservative, actually. And I'll throw out results which are flagged in any way by source extractor. So if you have that same sort of minimal goal set, it's pretty easy. But you can tweak all of those in the configuration file.
I'm curious, are there any major issues that it doesn't catch yet that you're hoping to add?
So other things that I'd like to add, I've got all the basics that I was shooting for at the beginning. I think it would be neat to construct a PSF from all the PSFs in every image so that you could look for, say, faint levels of scattered light in the background. So you could detect things like dust obscuration on the lens, whether you've got throughput issues there. I've even seen in some telescopes things like optical delamination of the coatings, which actually shows up in that way. That's going to be a little more work. Yeah, so that's sort of part of the package for the Visos project that I put up, because I couldn't figure out a way to do that generally that would apply in every case. But in that case, I just do a really sort of brute force method of going into a loop, waiting for an image to appear in a directory, dumping that to my measure image script, and then that, of course, goes to the Mongo database. So I've had collaborators that were, say, in Europe, and they're watching as the images build up on the web page within a minute after they're taken.
Well, thanks, Josh. Let's move on to the speakers.